Okay, let us give this a try again. The sound from the last lecture, it's pretty weird. It has a lot of noises. So I've tried to reduce the volume and maybe it would help. We'll see. Okay, so the last thing we did on Thursday, where many of you were absent, understanding again, was that we covered a bit of object-oriented programming, and we wrote a very simple program in the OP demo where I showed you that we can secure our data by making them private. Okay, these things are private, so they cannot be changed. Like the student ID, since this is private, you cannot just change a student ID after we have assigned a student ID to that through something called the constructor. We have constructed this object with student ID 113. We cannot change that, and this is a concept called what? Encapsulation. So the purpose of encapsulation was to keep our data secure, and this is what we have done. We cannot change the student ID, student name, the CGPA, the HSC GPA rather, but we can change the address because there is a method that allows us to do so, the set method right over here. So let me open the last design we had. Okay, so we have this UML class diagram, the Unified Modern Language class diagram, and over here what we got is the structure of this student class. We're going to design a lot of these things, these class diagrams, because we have to design first, then comes the coding, which is the secondary part. So this box right here lists all these attributes, and we have all these operations that we can perform on them, and we have achieved the encapsulation by putting this minus sign on this plus sign right over here. So encapsulation, the way it works, it uses something called the access modifiers. And in last class we talked about these access modifiers. It's just that I didn't mention the name. The access modifiers are private, protected, and public. So right now I've introduced only private and public. Private is these minus signs, and public is the plus signs. Okay, I haven't talked about protected yet. I didn't write any code that uses protected, and probably at this point it wouldn't make much sense to use protected unless I talk about inheritance and other package-related stuff. I will cover those, and when we do, I will come back to this thing, encapsulation again, and we will talk about protected. So for now, let us just talk about private and public. So this example that we have lets us create all these student objects, right? And if I comment out this line or delete this line, this would work. If you run this project, you'll see the student ID, name, address, and GPA right over here. And we can create another student, S2. We can instantiate that with the constructor, and then we can also print it over here. So this class, the student class, allows us to put everything together. The ID, the HSC GPA, the address, and the full name, everything together in one place. So the code is much more readable right now, and this is a difference from what we have done in C. We haven't created new types like that. We have learned to use the types that were given to us, like integer, short, long, character. Those things were given to us, and we were using them. It's just that now we can create new data types, and it's a fun thing to do. So what I want to do in today's class is to introduce some more OOP concept. In the last class we talked about a very important OOP concept, that was encapsulation. And in today's class, let me come up with a new problem, and I will show you another thing. So this is for OOP demo. I will keep it in the same place. What I want to do is to start a new diagram right over here, and just to give you an example what we will be doing, let us bring in this journal. It's easy to write there. I want to do simple arithmetic stuff which we have done before. So stuff like 2 by 3 plus 1 by 2. Can we complete this computation? What's going to be the result? 7 by 6. Okay, let us try this out. We need to find out the LCM, least common multiplicand, of 3 and 2, which is also the multiplication of these two numbers in this particular scenario. So this is 3 times 2. So 3 goes 2 times over here in 6. So 2 times 2 is 4. And 2 goes 3 times in 6. So 3 times 1 over here. Yes, you guys are definitely right when you said that this is 4 and 3 is 7. And this is 6 over here. So 7 by 6. We know how to do this. What are these numbers called? 2 by 3 or 1 by 2? Yeah, this is called numerator and this is called denominator. That's right. But as a whole, what is this number called?
Rational fraction.
Yeah, a rational number also, yeah, fraction is also correct. I will go with rational number because it makes more sense over here. Rational numbers are numbers that can be written as p by q, where p and q are integers. So this is a rational number. What is not rational? Can we give any example of that? 1, 2, 3, 4 is not rational. 1, 2, 3. This is actually rational because it can be written in this form. Okay, where 1, 2, 3, 4 is an integer and 1 is definitely an integer. That's why 1, 2, 3, 4 itself is a rational number. 2 by 1 is again a rational number. Just because we have a numerator greater than the denominator doesn't make it irrational. So these are not irrational numbers. However, e is an irrational number. It's never ending. It's going like that. Pi is never ending. It's going to go on like that. What about 3 point? Let me write it over here. We're not decided about it yet. 3.33 with a repeating symbol over here. So it's going to go on like 3.3333333 and so on. Is this rational or irrational? Irrational? Nope. This is a rational number because it can be written as 10 by 3. Where 10 is a integer over here, 10 is an integer, 3 is an integer. That's why this is going to be a rational number, because what we really need for rational number is p by q form. So just because we have an endless number of digits, it doesn't really make it irrational. The inability to write it as p by q, where p and q are integers, that's what makes it irrational. Okay, so is this thing clear? Now, why we're interested about rational number is because it allows you to do calculation without losing precision. If you write a number as a rational number, in the last example that we have, 10 divided by 3, if you use double or if you use float, you can only have a fixed number of digits. Okay. Just think about your calculator, and let me just show you right here. The calculator that I have on my operating system, if I use that to calculate 10 divided by 3, it shows the result in this format. I got 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 threes after the dot. Is this result correct? No, this result is not correct because there will be endless number of threes. So even if I add 30 more threes down there, it's not going to be correct even in that scenario. Okay. Because there will be more digits coming in, and I have a physical limitation. I have a physical limitation of space, how many digits I can show. So the calculators that we were using, the Casio calculators, maybe we can show 12 digits or 10 digits depending on the model. That also has the same limitation. Okay. And if you go into the actual representation of it, if you have done that in, let's say, computer fundamentals or numerical methods where we talk about the internal representation of numbers, you know that for floating point numbers we have the sign bit, the exponents, and the mantissa. So it's a fixed number of bits that you get to represent a number. That's why an infinite thing like this cannot be shown properly in that scenario. So with this particular problem, let's say I want to do a computation like 10 by 3 plus 2 by 3. Can we do that properly? We can't, because we will lose precision, and the result that we are going to get is not going to be correct. Yes, we can do rounding, but it can also make us lose precision. So, for example, we have 10 by 3, and if I want to add 2 by 3 to that, what's going to be the result? The answer is 4. But if you carry it out in a different way, for 10 by 3, if you write it as 0.33, sorry, thanks, 3.33, and if you write this one as 0.66, yes, I could round it up, but I'm just showing this because rounding can also be tricky. I get 3.99, which is not equal to 4. So we are losing precision over here. Okay, the calculation that we're doing is not right. Now the problem is, internally, none of our languages, C++, Java, or C, they don't support dealing with rational numbers. So what can we do? Okay. If you're going to write a program that does this computation, you're always going to lose precision, because there is no such support of writing numerator and denominator. And that's a problem. So to solve this, can we come up with a data type? Let me write a program. I mean, assuming that we have something like this. Let's say we have a data type now called rational number A. Okay, and we can declare another rational number B. So let's say rational number A equal to new rational number 10, 3 to mean 10 divided by 3. And we have another rational number that's 2 divided by 3. Wouldn't it be handy if we can save the result then into a rational number C equal to A dot add B? Okay. So if that's possible, that would allow us to add 10 divided by 3 plus 2 divided by 3 without losing any precision. It's just that we have to create this type. We don't have the type yet, but we can create this thing to come up with something as such. Is this thing clear? I mean, if we can do add, we can also do subtract, we can also do multiply, we can do divide. So all these things are possible only if we can write it in this format. So, in order to do this thing, I mean, I'm just showing you an example with code, but I don't want to do that. I don't want to write code first. Our approach here in this course would be to design this thing first. Okay, and then to do that, since we're creating a new data type, we will start with a class. All data types, they are classes, so this is our building block. And for those of you who were not here in the last class, I'm using a tool called Dia, which you can download and install on Windows as well. DIA, Dia. And over here, all these data types, we will come up with designs. And right now, you can see that what we are going to write is something called rational number. Okay. So the next thing you're going to ask is what are the things you need to keep for each rational number? That's one question. And the other question is what are the things you're going to do with those rational numbers? It's the same set of things we asked the other day, that we're going to create a new data type for a student, which is fine. This is our student data type. Okay, this is where we store all these attributes. What are the things to store for each and every student? And then we have the operations. What are the things you can do once you have the students? We can get the ID, we can get the name, we can get the address, and we can also change the address if need be. Okay. So let me ask you right over here, for each rational number, what are the things that we're going to store? Floating point. If you store the floating point, then we are back to the same problem, that we lose precision. So for example, 10 divided by 3, which is 3.3333. What are the things we are storing about this thing? Yes, the denominator and the numerator. These are the two things that you need to store about 10 by 3. Okay, there is no point in storing this dash. Means nothing, right? That's just a visual representation. These are the actual data that you need to store for this number. So 10 divided by 3, we need to store the numerator, we need to store the denominator, and then we'll do something about this. So if you realize that part, we can go into the attributes, and this is where we can write the numerator. Okay, so we need to store the numerator. What is the data type for numerator? Yes, so we can say long, no problem at all. We can also use integer, depending on how big a number you're dealing with. You can choose between long and integer. See, they are going to be whole numbers, because by definition, rational number says that any number that can be written as p by q, where p and q are integer numbers, it's a rational number. So I will go with your suggestion. Let us make it long. Okay, so we can declare that, and then we can get another one. And as you can see, right when you wrote that, we have plus numerator colon long. It is written in a very specific style, and they all mean something, right? What does this plus stand for? Public. Okay, it stands for public. That means that anyone and everyone can change the numerator if they want to, which we don't want, right? We want to keep our data secure. We want to put that into a capsule, which is called encapsulation. So we will make sure that all our data members there private. So let us change the visibility or the access modifier. Let us make it minus, and that means private. That's numerator. And in the same way, denominator, which is also long, and this is going to be private. So if you apply these two things, you see our box right in the middle where we write the attributes, it has changed. And now we can see numerator and denominator as two separate entries. They're both private. We can understand that from the minus sign. And it's written in a different way compared to what we do usually. We don't write long numerator as we would have done in C or Java. We have to write the name of the data type first, and then the data type itself after the colon. Okay. So given two rational numbers, what are the things that you can do with them? We can add two rational numbers, we can subtract two rational numbers, we can multiply them, we can also divide them. So, four basic operations. Let us write them down. I will just write the names first, then we will fix them. Add, subtract, multiply, and divide. Alright, so four methods that do four different things. Now, each of these methods, they are coming with a plus sign, so they are all public. Okay. What I want you to notice is that what are we going to get as a return type for each of these numbers? When we add two rational numbers, what is the output? Is that so? So right in this example, we have 10 divided by 3, we have 2 divided by 3. When we add them, what do we get? What is this? An integer. Okay, over here this is an integer. In this scenario, where we have 2 divided by 3 and 1 divided by 2, after we added them, what did we get? Okay, so if you write it as float, we are back to the same problem of losing precision. Okay. And this one over here is definitely not an integer. 7 by 6 is not an integer, it's not a whole number. This one definitely is a whole number, okay? But that is not a float, because if you write it as a float, you're losing precision. I mean, sometimes you can retain precision, sometimes you'll lose that. But in both the scenarios, you can find something very common. They can be written as numerator divided by denominator. Can we agree to that?
Yes.
If you take two rational numbers, if you add them, the result is going to be another rational number. Can we agree to that? Okay. So if that's the case, then we can say that this add method is of type rational number. So if you add rational numbers, you're going to get rational numbers as return. Now in terms of the parameters, this is a method. In C we were calling them as functions. In Java we just call them methods. So once we have these things, the add method, it's going to return us rational number. But what do we pass over here? That's the question. So if you look at the first example that I had with rational number, that we're going to create a data type and we're going to write programs in this way. This is the actual rational numbers a and b. So when we add them, we say a dot add b. How many parameters are we passing to the add method? 2 or 4? Actually, none of them. 1. 1. The parameter is in the brackets, in parentheses. How many things are we passing? Okay, just 1. So yes, I can understand both the answers. I can understand why you say 2, because we have two numbers, A and B. We need to pass them for them to be added. Yes, that makes sense. I can also understand 4 because there are 4 different things, numerator, denominator. Again, numerator and denominator for the other one. But that's something that comes from C. In C, we used to write programs like that. But over here, we're going to think differently. It's much more simple. See, the reason we need to pass only one parameter because one is already available to us. A is already available to us. Along with A, we are adding the other number. That's B. That's why it's one parameter, not 2, not 4. Okay. We will write a program, and you will soon understand that this is going to work. So the other number that we are adding is number B, which is going to be a rational number itself. Okay, so what is this add method like? It takes a parameter. What's the parameter? The parameter is B. And what type of parameter it is? It's a rational number. The actual function returns a rational number to you. That's what it says. Okay. I'm not going to write the subtract, multiply, and divide method right away. Well, for one reason, because they're exactly the same as the add method. It's just that the name is different. Because when you subtract one number from another, you need two rational numbers. A dot subtract B. So it's going to be one parameter that you pass. And the result of subtraction is what? Another rational number. If I subtract one rational number from another, I will get another rational number. So it's like integers. If I add two integers, the result is another integer. If I subtract one integer from another, that's again another integer. If I multiply two integers, obviously we're going to get another integer. If I divide one integer with another integer, that's when you can get float. Okay. So yeah, and it's not just obvious that if you're working on two things of the same data type, the operation will give you exactly the same thing. It can be something different. For example, for those of you who have done physics already, or actually it doesn't even need to. Do you guys know about vectors? Okay, you must have studied that in high school or school. It's covered in many different ways. If we have two vectors, if we do a cross product, the result is a vector. However, if you have dot product, the result can be a scalar. So it's not always that you have two things of the same data type. We do an operation, you get the same thing. I will start writing programs. It's just that I'm going to add two things over here. We got the add method. We need some support of printing because I want to print it on screen, whatever operation is happening. So something like a print method, which is not going to return anything. It will just print it out on the console. So there will be this print method. How are we going to use this? Let me show you right here. Say I want to print the result of C. I will say C.print. And the result will be printed on screen. That's what I mean. Okay. We also need to support the operations like this. That how can I create a new rational number? We do so with the constructor right when we call that. That's why we need something like this. And this is where we pass two parameters. Okay. So this is a special method which is the constructor. It gets called right at the beginning. How do we construct a rational number? We pass two things, the numerator and the denominator as parameters. Is this thing clear? Okay, so this is not complete yet. The design itself is not complete, but I think we have enough material to get started. Then we will add some stuff. I will come back to the design, I will update this, and I will also update my code. The idea that I was stressing on in our previous lecture on Thursday is that it always starts with the design. You're not going to jump into coding. Okay, you have to sit with your team, talk about the actual structure of this class and any other class, how they're going to behave, and then you're going to give it to the programmers who will actually write the code for you. Whoever is responsible to do that in the team. So, given that scenario, if we go back to writing a program, so this was about this is the first example in our OOP demo. We have this student type. Now, what I'm going to do is I will just create a new file. It's going to be a new Java class, and this is where this is going to be about rational number. So I will try to keep this thing on the side, just so we can see what we are doing and how these things are closely related. Okay, so we will have this design over here, and I will write the code over there. So what do we have? We have numerator and denominator, right? Now we cannot write stuff like this. We cannot write numerator colon long. We cannot write that in Java. This is UML class diagram. You need to know the distinction. It doesn't work over there. We have a different syntax. What we write there, the data type first, then the name. There's no place for this colon. We missed one thing, the minus sign, private. Okay, so that's the first line. What would be the second line? Thank you, private long denominator. So we are done with these two. Okay, let us do this one as well. Rational number, we pass two parameters. That's the constructor. Is it going to be public or private? Public, because we have a plus. Public rational number, and then we pass two things: long numerator, long denominator. Now I wrote them for a purpose in this particular way, that this numerator that we got, it's going to be placed over here. The denominator will be written to the denominator. So we can write something like numerator equal to num. Is this thing clear? Okay. So let us try one more thing. The print method, public. What's the data type? The return type? Void. If it doesn't return anything, then it's going to be void. It's supposed to print whatever we have in numerator and denominator. How do we do this? In Java, we write system.out.printf %d, that's a integer number, divided by, we're going to put a slash, and then another integer, %d, followed by a new line. And what are the two arguments we are passing? Num and den are local, so they don't exist outside this. What we have is numerator and denominator. Okay, so just armed with these two things, let us try this out. This is an example where we had the student type. So let me come down over here and create this rational number, a equal to new rational number, and this is where we pass 10,3, for example. And without doing anything else, I just want to print it out. So I say a.print and we get 10 by 3. So this is sort of working right here. Is this thing clear? Might be difficult for you guys at the back, but this is what we have. 10 divided by 3, that's the first number we got. Okay? So we'll see how we can write the add method, the subtract method, and everything else based on this idea. So this was not possible before we had a rational type. Now we have a rational number type and we can write stuff like this. Okay. Now one thing I want you to understand is I purposefully wrote these two things as num and den so that I don't get a naming conflict. I'd have loved to write it in this way, denominator. Okay, but now the compiler will get confused. So let me show you something that the IDE can help you understand what you're working with. Whenever you put your cursor on a particular variable, NetBeans IDE or any other IDE for that matter, the advanced ones, they will actually highlight all the occurrences of that. So that's a visual cue. You see num is this one. If I take my cursor to den, it will show you exactly all the places where this thing is used. Okay? If I put my cursor over here, it shows you all the places where denominator is used. Is this thing clear? The visual cue itself. So now when I say numerator, and if I change the name because it doesn't exist, num doesn't exist anymore, what happens? Which variables are selected? Only these ones, right? Numerator, numerator, numerator. How about these numerators? They are not selected. That tells you that whatever variable you pass is only local over here. You're going to write this value back to here, not affecting this one, because they are not related. Alright. Previously, it was not a problem when I had a different name. For example, let us just make the name different, and you'll see. This is numerator 1, and if I take my cursor over here, I get all these things highlighted. But as soon as I change this one, the compiler gets confused because it doesn't know which one to relate to. Okay. There is a fix for that. This. In Java, when you say this dot, it means the attribute of the current object or the method of the current object, anything that belongs to this current object. Okay. So this dot numerator is this thing. What about this one? The one that comes as parameter? That's a different thing. This is mine, all right? Whatever I have in the class is what I refer to with this. Whatever comes as parameter will be without this. Okay. So again, let us look at this denominator. See, these things are highlighted, but as soon as I change the name to denominator, then it's only local. It's not going for all these things. The way to fix that is with this. As soon as you do that, there is a clear distinction. One is without this and the other one's with this. So this is the denominator. Okay. Our program will work as it did before. So what's the advantage to this? You don't have to come up with new names. You can use the existing names. It's just that to make a clear distinction, we add this whenever we are referring to members of the current class. Okay. Now the other reason why I wanted you to understand it is because since we're using an IDE, integrated development environment, a lot of these programs we don't even have to write. This is a constructor, right? I can get the IDE to write it for me. I don't have to write this. Take your keyboard. If you hold down Alter and press Insert, Alter plus Insert, that brings out this generate menu. You have to be inside NetBeans in a class. Alter Insert will bring in this generate menu. And over here, what do I want to generate? A constructor. What are the parameters I want in there? Numerator and denominator. So you can take your mouse and click over here, or if you're more familiar with the keyboard, just press spacebar and then go hit generate, and it writes the exactly same method for you, so you don't have to do that. Okay. Maybe it wouldn't mean much right at the beginning, but let me modify this thing. Okay. So what are the things we got in this class? We got a constructor that takes 4 attributes. We got some methods to get the student name, student ID, HSC GPA, address, and we got one method for the set address. Right? This is all we did, and we had to write all these codes by ourselves. Okay. But look at this: the get student ID, get student name, get HSC GPA. They have a very clear and easy pattern. You have to write return student name, return student ID, return HSC GPA, and all that. So it's very easy to write, but it is also tedious. You'd have to type it in by yourself. Since we are using an IDE, we don't have to do any of that. Okay. So we need to declare all these things. The attributes, definitely we have to write them by ourselves. But the constructor, if you need them, NetBeans can write it for you. Okay, like I did before. We needed the get methods, alter, insert, get the getters. I need getter for all these things. So I've checked everything. And hit generate. So here comes all my get methods. And finally, the set method, I don't want it for everything, I just want it for the address field. I just hit enter and there we go. I didn't have to write the program. Okay. So yes, it's a good practice to write it by hand, and that's what I want you to learn. But when we're moving into production, when we're writing a big piece of software, these things will just waste time. Why do it when you have features? So when you understand what's in there, you have to use the features from the IDE. Again, the shortcut to use is alter insert. You get a generate menu and you pick stuff from there. It's just there for you. All right, so we got this print method and the constructor, but we don't have the fancy stuff like add, subtract, and everything else. Okay. So first of all, if you look at the signature of the method, to add 2 rational numbers, we need to pass the second rational number. Which goes something like public. What's the return type? That's a rational number, right? And then what's the name of the method? Add. What's the parameter? B. And what's the type? Rational number. So this is where we'd have to find something, how to deal with this. So first of all, to add two rational numbers, you need two rational numbers to start with. We don't have that. We have this rational number b. So where is this rational number a? That's the question. If you look at the OOP demo, or the way we want to use this, let me create an example out here. We will have two rational numbers. One is a, the other one's b. So let's say one is 10 by 3, the other one's 2 by 3. We can print both the numbers, no problem whatsoever. But what we really want to do is declare rational number c as a dot add b. So here's this problem that somehow we have to write this add method. We started writing this. We pass b, but we don't pass a. We are calling the add method on a. A is already there. That's what you need to understand. B is the only thing that gets passed. So how do you write it in a program? When you have only the B part, you need to understand that whenever we talk about A, we already have this, which means A is this itself. The numerator and the denominator, we have them already. That's this. Okay. And what we need to send out is a rational number, c equal to new rational number. This is where we need to pass the numerator and the denominator, which we don't know about right now, but somehow we will find them. And once we do, we can return c. This is the structure of the program itself. We got a rational number, which is this, and the numerator and denominator is already available. We have another rational number, which is b, that would also have its numerator and denominator. And we are going to create a rational number called c, where we will have something. I'm just putting question mark over here as placeholder. This is something we need to compute. And once we compute that, we can return c back to the caller. Is this thing clear? That this is going to be our workflow? If you have any question, let me know. I mean, can't really go ahead without clearing this out first. See, the example that we are trying to work with, let me take a screenshot. I think it's easier explained with a picture. Alter, where's my print screen? Okay. Save. Can I not use this? File, open. Yeah, probably not. Okay, I'm downloading a tool that I'll need to annotate stuff. It shouldn't take much time. And there we have it. Okay, so I'm just going to open the picture that I saved so that I can write stuff over here. Okay, so we're going to write this add method, right? And let me use a different color just because I got pictures here. So as B, what we are passing is 2 divided by 3. Okay. How do you know this? You know that from the main method. B is 2 by 3. And what's A? 10 by 3. So that 10 by 3, there is no A over here. It says it's this. What does this mean? This means whatever you have here. And that's actually 10 by 3. Okay? So that's why we write this A as 10 by 3. And now we're going to create rational number C. It's a new thing. And how do we do this? C is equal to 10 by 3 plus 2 by 3. Okay? And this can be written as A dot numerator, I'm not going to write the whole thing, I don't have space for that, divided by A dot denominator plus A dot, not A dot, B dot numerator divided by B dot denominator. So I'm just replacing these real numbers with the labels, the numerator and denominator. Now, can we carry out the operation? What do we get for denominator? The denominator over here is 3 in both the cases. So what's the LCM of 3 and 3? 3, okay? But calculating the LCM itself, that may be a little bit difficult. For now, let us go with something simpler. Instead of calculating the LCM, can we simply multiply them? Okay. It's going to produce a different result, but not a wrong result. It's still going to be correct. So if you write it like that, it's going to be 3 times 3 as 9. What do we have? 3 goes 3 times in 9, so we multiply 10 with 3. That's 30. And over here, 3 goes 3 times in 9. So we multiply this with 3 again, we get 6. So what I'm saying is, let us make our life a little bit easy. Let's just say that to calculate the numerator and denominator, let me write it as N for numerator, and well, I will fill it in a bit, and D for denominator. What's the denominator? That's the easy part. We multiply these two things, right? Which means we multiply A's denominator with B's denominator. So can we then do A dot denominator into B dot denominator? We can do that, right? So for C, what's going to be the denominator? D. That's how we can replace this right over here. How about the other part? How do we calculate the numerator then? A dot numerator times B dot denominator plus B dot numerator into A dot denominator. Okay, because that's going to tell you how many times can you divide the multiplication of 3 and 3 by A dot denominator. The answer is this. That's why you multiply with this number. So A's numerator times B's denominator plus A's denominator times B's numerator. And that you can put in right over here. That's our add method. Once everything is in place, we get A, we get B, and this is C. Is this correct? Well, actually it is correct. We were supposed to get what? 4. 36 divided by 9, that's actually 4. We just have to reduce that. We didn't reduce it. We didn't divide both the numerator and denominator by what? By the GCD. If you do that, then it's going to be 4 divided by 1, which is the answer. So we're almost there. Just we are left with the reduction part, but that's a different story. Is this thing clear? Yes. If we understand this part, writing the subtract, the multiply and divide method, it's not going to be that difficult. Okay. How soon? Let us write a few of these. Let me go back to the design, the class diagram, the subtract method. Now you know what to do, right? Subtracting one rational number from another, what do we get? That's the return type. What are the parameters? We have to pass only one parameter, and that's going to be a rational number. The other rational number we have in our hand already, so we can just hit OK, and that's our subtract method. Okay. How do we write the subtract method over here? Okay, I could just copy paste the whole thing, but let me type it out. The return type is going to be a rational number. The name of the method, subtract. The parameter is going to be another rational number. Okay, so A is this. We got one rational number, and the other one came as parameter. The numerator that we get as A's numerator. So we're at A dot numerator times B dot denominator. And previously for the add method, we added them up. And this time we need to subtract. So we put a minus sign, denominator into B dot numerator. And then the denominator part is going to be long D equal to A dot denominator into B dot denominator. And what else? C equal to new rational number, numerator and denominator, you pass them along, and then we return this thing out. So just to test this out, let me change this thing. Subtract works fine, right? 24 by 9, that's the answer. Okay, so what about multiply? Multiplying two rational numbers, that's even easier than adding, right? Or subtracting. You just multiply the numerators and then the denominators. So that's that. I'm going to leave this thing for you then. How to write the multiply and divide. It's your task to modify the design over here, multiply and divide, and then implement that in the code itself. Okay. So whatever you learned in primary school, you're just going to write the same thing, just in Java. So once we have that, it's going to be quite an advantage for us, because now we have a type that allows us to do calculation without losing precision. We're not writing it as floating point numbers. We're being able to add stuff. We're going to be able to subtract stuff with fractions or with rational numbers, just in this form. All right, so that's one of the things. And I'm going to come up with another very similar example just to reinforce this idea. So we know about this rational number, and for at least some of you, I think you also know about complex numbers. Okay, and before I go any further, let me just give you some examples of what complex numbers were. So something like 2 plus 5i, that's a complex number. And let's say I got 4 minus 2i, that's another complex number. We can add them, we can subtract one complex number from another, we can multiply, we can also divide. Now, if we have two complex numbers like this, these thing, this 2 and this 4, these are called the real part. And this 5 and 2, 5 and minus 2 rather, that's the imaginary part. How many of you haven't seen complex numbers before? Anyone? Okay, so that's good. We have seen complex numbers. Now, I'm not going to give you any test that you have to do maths here. Okay? If you forgot the rules, well, that's fine. We are going to relearn them again. What's this I? Square root of minus 1. That's what I is. Okay? So how do we add two complex numbers? You add the real part and the imaginary part separately. So 2 plus 4, that's 6. That's going to be the real part. And for the imaginary part, you get 5 plus minus 2, which is going to be 3i. So 6 plus 3i, that's going to be the answer for addition. So addition and subtraction, they're very similar. Add the real parts or subtract this real part from this one, that's for subtraction. Subtract the imaginary part from the imaginary part, that's what subtract is. So add and subtract, they're really easy to do. Multiply, well, that's where things get a little bit interesting. Divide, that's a bit more fun. Okay. So we will get there. I will write those for you, but let us get started with at least this concept thing. We don't have a data type. We have int, we have double, we have long. We don't have complex. Not in C, not in Java, not in C++. At least not as primary data type. So we have to create our new data type for ourselves. And that's where this dia will help, that we're going to create a design. And as for attributes, what are the two attributes we got? Real part and the imaginary part, right? Now, what should be the data type for real? What would be for imaginary? See, previously we had this advantage in rational number that we could say that P and Q, they all will be integer data types, but no one's saying that for rational, the complex numbers. For complex numbers, these can be floating point numbers. As such, let us just leave them as double. Real can be double, like we can have 2.33 plus 5.65. So this can be private. Imaginary can be of double type, that's also private. Okay, and as for the operations that we want to perform, let us start with a very simple one. We want to write a add method which is going to return what? If we add two complex numbers, what's the result? A complex number. But over here, just like rational numbers, we need to pass one number because the other number is already available to us. So we're going to pass a complex number over here, and yeah, hit OK. All right. We will have a bunch more methods, but let me write the very obvious ones. We need a constructor, so we will have something like a complex number where we pass what? The real part and a imaginary part. So when that's done, we have our constructor, and we need one more method just to test out. We will have our print method, which is not going to return anything. That's why this is left as void. So this is the basic design, right? We will have a few more methods added to this, but right now this is all we need. Okay. I'll try to write at least the add method for you before we are done with the class. But let me save this thing, or I'll forget to do it later on. So I have another diagram. Let me just call this numbers.dia. And yeah, right here we are going to create a new data type now. Every time we create a new file, we go for this white plus sign, or you can go to the file menu to create a new file. This is going to be a Java class. We're going to call this complex number, and right here we have, if you look at this picture, we have two attributes, real and imaginary. So we write private double real. Thank you. Private double imaginary. How do we write the constructor? Alter insert, or you write it by yourself, whichever way you go. Like, I'm trying to save some time, so yeah, that's that. We got the real and imaginary. That's the constructor for you. And we need to write the print method. Public void print. How do we print this? We can print this with system.out.printf. We will print the real part, which is a floating point number, and let us decide that we are going to print 3 digits after the dot, or you can print as many digits as you like. This plus the imaginary part, which is going to be, let's say, another 3 digits, followed by I for square root of -1. And what are the things we pass? The real part and the imaginary part. So that's the print method, right? How do we write the add method? What are we going to return? We are going to return a complex number. What's the name of the method? Add. What's the parameter? Which is another complex number. So this is what it is. The first complex number that we have in our hand is complex number A, which is this. And then we are going to add B to that. So let us create the result over here. Complex number C equal to new complex number real and imaginary. R for real and I for imaginary. Okay, we will fill that in, and once we are done, what do? Return C. So if you understand rational number, you'll see that we are writing in very similar way, right? Only a few things will change from one code to the other code. So for complex number right here, we're following the same pattern. We got B, we got A. We're going to do some calculation. How do you find the real part in addition? This is add though. Real plus real. So 2 plus 4, real plus real. Alright, so A dot real plus B dot real. And down here, A dot imaginary plus B dot imaginary. So we got that, and we are passing that to create a new complex number, and everything should work just fine. So in our demo, let us create this complex number x equal to new complex number. Okay, So this is going to be 2 and 5, according to the example that we have set up. 2 plus 5i, and the next one is 4 minus 2i. Okay. So let us copy and paste this. This is going to be our new complex number. This is going to be 4 and minus 2. And then we can have complex number z equal to x dot add y. And we are almost there. So we just need to print them out. Like x dot print, y dot print, and z dot print. So if you run them now, what do we have? We have a really ugly thing because I forgot to put new lines over here. If you look at the output, they're all in the same line. It's hard to track. So with the new line in place, 2 plus 5i, 4 minus 2i. If you add them up, 2 plus 4 is 6, and 5 minus 2, that's 3. Is this thing clear? Okay. So I haven't done a lot of things. Like I haven't written the subtract method, the multiply or the divide method. We will talk about them in the next class because we are running out of time. Yeah. Time is already over. So I will upload the code into our Bitbucket repository. I gave you a link to that repository through our classroom. It was in the lab class. We had a lab class in lab 3. I showed you how you can download these things. I'm going to upload all these things to the same place so that when you go back, you can download these things. Okay. What I want you to try out as homework is to write all other methods. Subtract, multiply, divide for both these classes. Okay? Try them out so that we can discuss them in our next class. I don't want to spend too much time going through this. So let me know what worked for you, what didn't, and whatever you do, make sure that you just put it out by some random numbers. Do some calculation by hand, see if the result matches or not. Stuff like that. Okay. Any question about any of these things or anything else? Okay, all right, thank you guys. I need the attendance sheet back though.